In this video, I'm going to show how to use the definition of the Laplace transform to find Laplace transforms of some elementary functions. So here we're going to find the Laplace transform of a quadratic term, an exponential term, a trigonometric term. Then we're going to give you the opportunity to find the Laplace transform of a linear term, a hyperbolic function term, and a product of a linear term times an exponential term. So this is just going to be involve integration basically. So let's get on with the first one. So in the first one, we're looking for the Laplace transform of t squared. So this is going to be the integral of, so we're simply going to plug in t squared here. So that is going to be t squared e to the minus st dt. So remember, s is a positive parameter. So this can easily be evaluated using tabular integration. If you're not familiar with that method, I'm going to post a link right here that is going to take you to our video that does a detailed description of that method. But basically, we take the polynomial and differentiate it to 0. So derivative of t squared is 2t, derivative of 2t is 2, and derivative of 2 is 0. Then we take the exponential and integrate it repeatedly. So the integral of this one is going to be minus 1 over st e to the minus st. This one is going to give us 1 over s squared e to the minus st. This one is going to give us negative 1 over s cubed e to the minus st. Then we multiply the first with the second with the third, etc. The first product is always goes with a positive sign. So what's going to happen here is therefore our Laplace transform of t squared is going to be so this group of terms is going to be negative. This one is going to be negative as well, and that one. So all the terms are going to be negative. So then we're going to have t squared over s plus 2t over s squared plus 2 over s cubed. All of them are multiplied by that between 0 and infinity. So when we plug in 0 here, this term will vanish, this term will vanish, this term will remain, this will be 1. So when we plug in 0, we're going to get 2 over s cubed, and that is going to be positive because of this negative here. But then the limit at infinity, so we evaluate that one by taking the limit as t goes to infinity of this thing. So it's going to be t squared over s plus 2t over s squared plus 2 over s cubed. Now what's going to happen with this thing is that this term, this whole term here, t goes to infinity, is going to go to infinity, while this other term is going to go to 0. So the question is which term is going to dominate which term, and by L'Hopital's rule we can show that this term is going to dominate. Actually just check our next video after this one. Then you are going to demonstrate this. So this is simply going to work out then to 2 over s cubed. Okay, now just to get a picture of what's happening here. So what the calculation is telling us is that if we start off with t squared in the t space, so t squared is going to look like this. Remember, we are only interested in the part of the function where t is positive. So the calculation shows us that this gives us the transformation 2 over s cubed. So this is the t space, this is the s space. So that's f of t this side and f of s this side. So we're getting from here to there through the Laplace transform. So this function, which is an increasing function, gives us that function which is a decreasing function. So that is part A. So if we go to part B, there we have got f of t equal to e to the at, where a is a constant. So the Laplace transform of this is going to be the integral of e to the at times e to the minus st from 0 to infinity. Without any loss of generality here, we are going to assume that a is smaller than s. We can always manage to achieve this unless a, of course, is infinity, which it is not. So this thing is just going to be, we can write it as e to the negative s minus a. So with that assumption, that tells us that this is going to be a positive number. And then if we integrate this, so this is simply going to be e to the minus s minus at divided by a minus s between 0 and infinity. So again, if we let t goes to infinity, this whole term is going to go to 0. So just write this as so for the top limit, as that goes to infinity, this is going to go to 0, and then as t goes to 0, or at t equals to 0, of course, that is going to be -1. So that means the Laplace transform is going to be 1 over s minus a. So that is the Laplace transform of e to the at. And then going to C, we have got our function is cosine of at. So again, if we just plug this into the integral, so it's going to be the integral of 0 to infinity cosine at e to the minus st dt. There are at least 2 ways of integrating this. I am going to use the complex approach. So I'm going to just for the time being focus on the indefinite integral. So cosine at e to the minus st. This we can write as the real part of the integral of e to the ait times e to the minus st. And then, of course, this is the same as the integral of e to the ai minus s times t. This we can integrate readily, not a problem. It's going to be e to the ai minus s divided by ai minus s. So remember, s is a real quantity. So then we need to write that in terms of real part and imaginary part. If we extract the e to the minus st, then this is just e to the ait over ai minus s. But then e to the ait is just cosine at plus I sine at. Now, for us to be able to extract the real part of this, we need to remove the imaginary term from the denominator, and we do that by multiplying by the complex conjugate of the denominator. And so we multiply both numerator and denominator by that. So when we do that, so this is what we are going to get. The real part is going to be, so let's see what's going to happen here. So if you multiply s, negative s by cosine, that's going to give us a real term, and then ai, negative ai times this is going to give us a sine at. So those terms are going to be real. And then the other terms, just for completeness sake, are going to be a cosine at plus s sine at. But our main interest really is in this one here. And the denominator, of course, is going to be this times this. It's going to be a squared plus s squared. So if we extract the real part of this, it's going to be e to the minus st over a squared times plus s squared. Then this is going to be times a sine at minus s cosine at. So that is going to be the integral of this. Okay, so here, of course, we have used the Euler's formula, e to the I theta is cosine theta plus I sine theta. So real part of this is just cosine theta. So that's what we've done from here to there. This term is real, of course, so real part of it just remains the same. So, but real of this is just cosine. So then we need to apply the limits. So the Laplace transform of cosine of a t is going to be e to the minus st over s squared plus a squared times a sine at plus s cosine at 0 to infinity. Now as t goes to infinity, this term goes to 0. These terms just remain between 0 and 1. So that means as t goes to infinity, this whole thing is going to go to 0. And then minus when t is 0, this is going to be 1. It's going to be 0. This is going to be 1. So that's just going to be s over s squared plus a squared. All right. So at this point, we're going to give you an opportunity to have a go at these last three here. So you can just pause the video, work through them, and then you can compare your answer with our solutions. All right, we're now going to scroll down to our solutions for D, E, and F. We're hoping that this material is useful to you. Please do not forget to subscribe to our channel. And if you've got any questions and comments, please post them in the comments section. All right, so for part D, we have got the Laplace transform of t. So if you plug into this integral, this again can be evaluated using tabular integration. And so we have got this situation here. As t goes to infinity, this goes to 0, this goes to infinity, but this dominates the whole situation, so that's going to be 0. And then when t is 0, this term vanishes, so we're just going to have 1 over t squared. So in fact, in general, the Laplace transform of t to the power n, where n is a positive integer, is n factorial over s to the power n plus 1. We're going to prove this by mathematical induction in the next video. For E, Laplace transform of hyperbolic sine of a t, we'll write this in terms of exponentials and then remove the brackets. So again, here we have assumed that a is smaller than s, so this is a positive number. So that means as t goes to infinity here, this term goes to 0, so does that one. So the only terms that are going to survive is when t is 0. So we're going to have these two here. If we combine these into one fraction, then that gives us the Laplace transform of hyperbolic sine of a t. This time we've got t times e to the minus a t. If we collect terms here, then we can integrate using tabular integration again. So as t goes to infinity, this goes to 0, dominates this one which goes to infinity. So the only term that's going to survive is when t is 0. All right, so it brings us to the end of that. Thank you for watching.